Welcome to this video on solving LeetCode problem number 2111, minimum operations to make the array k increasing. In this problem, we aim to determine the minimum number of operations needed to transform an array so that every kth element forms a non-decreasing subsequence. We'll explore the problem step by step, discuss potential approaches, and analyze their complexities. Let's dive in. In this problem, we are tasked with transforming a given integer array, RR, into a k-increasing array with the minimum number of operations. A k-increasing array is defined as one where, for every valid index I, the condition ARR, I equals RR, I plus k, holds true. This means each element must be less than or equal to the element located k positions ahead of it. To achieve this, we are allowed to modify the array by selecting any index I and changing ARR, I, to any value of our choice. The goal is to determine the fewest such modifications necessary to make the array satisfy the k-increasing property. The input consists of the array ARR and the integer k, and the output is the minimum number of operations required. The constraints ensure that the array can have up to 100,000 elements, and each element can have a value as large as 1 billion. Let's now explore some examples to better understand this problem. Consider the first example, where the input array is 5, 4, 3, 2, 1, and k is 1. Since k equals 1, the condition simplifies to ARR, I equals RR, I plus 1, for all valid indices. However, this array is strictly decreasing, so every element violates the condition. To make it non-decreasing, we can perform the following operations: replace ARR 1 with 5, resulting in 5, 5, 3, 2, 1, then replace ARR 2 with 5, giving 5, 5, 5, 2, 1. Next, replace ARR 3 with 5, resulting in 5, 5, 5, 5, 1, and finally, replace ARR 4 with 5, yielding 5, 5, 5, 5, 5. In total, we perform 4 operations to make the array satisfy the k-increasing condition. Thus, the output is 4. Now, let's examine a second example with the array 4, 1, 5, 2, 6, 2, and k equal to 2. Here, the array can be divided into 2 interleaved subarrays based on k. The first subarray consists of elements at indices 0, 2, and 4, which are 4, 5, 6. The second subarray includes elements at indices 1, 3, and 5, which are 1, 2, 2. To satisfy the k-increasing condition, each subarray must be non-decreasing. For the first subarray, 4, 5, 6, no modifications are needed since it is already non-decreasing. For the second subarray, 1, 2, 2, we need to replace ARR 3 with the value 2 to maintain a non-decreasing order, resulting in 1, 2, 2. This requires just one operation. Adding the operations from both subarrays, the total number of modifications is 1. Therefore, the output is 2. Let's look at a third example with the array 4, 3, 2, 1, and k equal to 2. As before, we divide the array into 2 interleaved subarrays. The first subarray consists of elements at indices 0 and 2, which are 4, 2. The second subarray is formed by elements at indices 1 and 3, which are 3, 1. For the first subarray, 4, 2, we need to replace ARR 2 with 4, resulting in 4, 4. For the second subarray, 3, 1, we replace ARR 3 with 3, yielding 3, 3. Each modification involves one operation, so the total number of operations is 1 for the first subarray and 1 for the second subarray, leading to a total of 2. The output for this example is therefore 2. When solving this problem, it's essential to consider various edge cases. For instance, if the array has only one element, it is already k-increasing, and no operations are needed, so the output is 0. For large arrays with up to 100,000 elements, efficient algorithms are necessary to avoid performance issues. Techniques like dynamic programming combined with binary search can help achieve this. Another edge case arises when all elements in the array are equal. In this situation, the array is already k-increasing, so no changes are needed, and the output is 0. Finally, when k equals the length of the array is treated as a single subsequence, and the task reduces to making the whole array non-decreasing. These considerations ensure that the solution is robust and handles a wide range of scenarios effectively. To tackle the problem of making an array k-increasing, we initially explored the brute force approach.
The intuition here is straightforward. For every valid index in the array, we check if the k-increasing condition is violated, specifically whether the element at index I is greater than the element at I plus k.
If it is, we adjust the array by incrementally replacing the out-of-place element to restore the condition. While this method is simple and easy to understand, it requires nested loops to check and modify the array, resulting in a time complexity of n squared. This makes it highly inefficient for large arrays, especially when the input size can go up to 10 to the power of 5. Thus, while the brute force approach is conceptually clear, its computational expense and lack of scalability make it impractical for competitive settings. A more efficient strategy involves reducing the problem to finding the minimum operations required to transform specific subsequences of the array into non-decreasing sequences. This is where the concept of the longest non-decreasing subsequence, or LNDS, comes into play. The key insight is that minimizing changes in a subsequence is equivalent to maximizing the length of its LNDS.
To apply this, we group the array elements using their modulo k indices. For instance, one group might include elements at indices 0, k, 2k, and so on, while another group includes elements at 1, 1 plus k, 1 plus 2k, and so forth. For each group, we compute the LNDS efficiently using binary search combined with dynamic programming, which operates in m log m, where m is the group size. The difference between the total elements in the group and its LNDS length gives the number of modifications needed for that group. Summing these results across all groups yields the total number of operations for the entire array. With a time complexity of n log n/k, this approach is both efficient and scalable. The optimized approach using LNDS is our chosen solution strategy, primarily because of its efficiency and its ability to break the problem into smaller, independent subproblems. By dividing the array into groups based on their modulo k indices and solving each group optimally, we ensure that we minimize the number of operations required. This method avoids the inefficiencies of the brute force approach, which redundantly modifies the array and repeatedly checks conditions. Instead, LNDS allows us to preserve the maximum number of elements in their original positions, minimizing changes. This makes the solution not only computationally efficient but also elegant in its design. While the brute force approach may seem easier to implement, its n squared complexity renders it unsuitable for larger arrays, where performance and scalability are critical considerations. The optimized approach, grounded in LNDS, stands out due to its significantly improved complexity of n log n/k. While it requires a solid understanding of binary search and dynamic programming, the benefits in terms of performance are substantial. By leveraging this method, we achieve both correctness and efficiency, making it ideal for handling large input sizes. This approach demonstrates how a deep understanding of the problem structure can lead to a dramatic reduction in computational cost, enabling us to solve the problem effectively within competitive programming constraints. Thus, the optimized LNDS-based strategy not only meets but exceeds the requirements of this problem, making it the clear choice for implementation. The problem minimum operations to make the array k increasing challenges us to transform an array so that it satisfies the k increasing condition with the fewest possible changes. This condition means that for every index I in the array, the value at arr I must be less than or equal to the value at arr I plus k. To solve this efficiently, we can break the problem into smaller, independent parts. The first step is to divide the array into k independent subarrays. For instance, if k is 2, the array is split into two groups, one containing the elements at indices 0, 2, 4, and so on, and the other containing elements at indices 1, 3, 5, and so on. Each of these subarrays is independent of the others because the k-increasing condition is satisfied within each subarray. This division allows us to solve the problem for smaller pieces rather than the entire array at once. After dividing the array into k subarrays, the next step is to transform each subarray so that it becomes non-decreasing. This is where the concept of the longest non-decreasing subsequence, or LNDS, comes into play. The LNDS represents the largest subset of the subarray where the values are in non-decreasing order. Any element already in the LNDS doesn't need to be changed, while elements outside the LNDS do. So, the number of modifications required for a subarray is simply the total number of elements minus the length of the LNDS. To find the LNDS efficiently, we use a greedy algorithm combined with binary search. Instead of explicitly constructing the sequence, we maintain a dynamic list of potential sequence endpoints. As we iterate through the subarray, each element either replaces an existing value in the list or gets appended to it, depending on where it fits. The length of this list gives us the LNDS size. The total operations for the array are then calculated by summing the required modifications across all k subarrays. There are several key insights that make this approach both effective and efficient. First, dividing the array into k subarrays simplifies the problem by breaking it into smaller, independent challenges. This way, we only have to solve the k increasing condition within each subarray. Second, transforming a sequence into non-decreasing order is reduced to finding the LNDS. This eliminates the need to explicitly sort or update the array, which would be computationally expensive. The efficiency of our algorithm comes from using binary search to compute the LNDS, allowing us to handle each subarray in n/k log n/k time. For data structures, we rely on a dynamic list to store potential endpoints for the LNDS and array slicing to generate the k subarrays. Together, these components ensure that the algorithm is both fast and memory efficient. Now, let's analyze the complexity of this approach. For time complexity, dividing the array into k subarrays takes n. Calculating the LNDS for each subarray is n/k log n/k, and since there are k subarrays, the total time complexity becomes n log n/k. For space complexity, the dynamic list used to compute the LNDS requires n/k space for each subarray, and since there are k subarrays, the total space usage is n. To illustrate the algorithm, consider the example where the input array is 5, 4, 3, 2, 1, and k equals 2. First, we divide the array into two subarrays, 5, 3, 1, and 4, 2. Then, for the first subarray, the LNDS is 3, meaning two elements need modification. For the second subarray, the LNDS is 2, requiring one modification. These calculations give us the number of operations needed for each subarray. Finally, we sum up the modifications from all subarrays to determine the total operations required. In this example, the first subarray required 2 modifications, while the second subarray required 1. Adding these together, we find that the minimum number of operations needed to make the array k increasing is 3. This result demonstrates how the algorithm efficiently combines subarray division and LNDS computation to solve the problem in optimal time. By leveraging these key insights and data structures, we achieve both accuracy and scalability, making this approach suitable even for large arrays. The provided solution efficiently solves the minimum operations to make the array k increasing problem. The first step is to define the length of LNDS function, which computes the length of the longest non-decreasing subsequence, LNDS, for a given subsequence. This function uses binary search via bisect_right to maintain an efficient n log n complexity. The main function min operations begins by initializing operations to 0, which will store the total number of operations required. It iterates over each starting point within the range 0, k, treating elements at indices separated by k as independent subsequences. For every such subsequence, the LNDS length is calculated, and the number of operations required to convert the subsequence into a non-decreasing sequence is the difference between its length and the LNDS length. This value is added to the operations counter. Finally, the function returns the total number of operations required for all subsequences. The overall algorithm runs in n log n, making it efficient even for larger input arrays. This solution handles edge cases such as small arrays, large values of k, and arrays that are already k increasing. Here, we begin with the Java implementation of the solution. The main method is min operations, which takes the input array arr and the integer k. First, we determine the length of the array and initialize a variable operations to 0. This will keep track of the total changes needed to make the array k increasing. Next, we use a for loop with a step size of k to divide the array into groups. For each starting point in the range of k, we extract a subsequence consisting of the elements at every kth index. Once we have this subsequence, we calculate the length of the longest non-decreasing subsequence, or LNDS, using the helper function length of LNDS. The number of operations required for this group is the size of the subsequence minus the LNDS length,
which we add to our total operations count. Finally, the method returns the total operations needed.
The length of LNDS function begins here and is defined to calculate the LNDS for a given list. The length of LNDS function uses a dynamic approach with binary search to compute the length of the longest non-decreasing subsequence.
For each number in the subsequence, we find its position in the current LNDS using the binary search right helper method. If the number is larger than all elements in the LNDS so far, it is added to the list. Otherwise, we replace the element at the found position to maintain the smallest possible sequence that is still non-decreasing. This ensures that the LNDS is as efficient as possible. The function then returns the size of the LNDS list, which represents the length of the longest non-decreasing subsequence. Now, let's look at the details of the binary search right method, which is used to determine the position of a number within the LNDS. The binary search right method performs a binary search on the given list to find the correct position for the target value. It initializes two pointers, low and high, to define the search range. The method iterates while low is less than high, calculating the middle index and comparing the value at this index with the target. If the value is less than or equal to the target, it narrows the range to the right half by updating low. Otherwise, it narrows the range to the left half by updating high. Once the loop completes, the value of low represents the insertion point for the target in the LNDS. This method ensures that we efficiently maintain the smallest possible non-decreasing sequence, which is critical for optimizing the solution's performance. Finally, the result of binary search right is returned to the calling function. Here, we begin with an example where the array is 5, 4, 3, 2, 1, and k is 1. The goal is to make the array k increasing with the minimum number of operations. Since k equals 1, all the indices are part of the same subsequence, which means the entire array, 5, 4, 3, 2, 1, is considered as one subsequence. To solve this, we need to find the longest non-decreasing subsequence, or LNDS, within this subsequence.
Starting with an empty list, we iterate through the array.
First, we add 5 to the LNDS, then replace it with 4 as 4 is smaller. Similarly, we replace 4 with 3, then 3 with 2, and finally 2 with 1. By the end, the LNDS contains only 1 and has a length of 1. Since the length of the LNDS is 1 and the original subsequence length was 5, the number of operations required is 5, 1 equals 4. This means we need to modify 4 elements in the array to make it k increasing. Now, let's consider another example where the array is 4, 1, 5, 2, 6, and k is 2. In this case, we divide the array into two subsequences based on the value of k. The first subsequence includes indices 0, 2, 4, which corresponds to 4, 5, 6. The second subsequence includes indices 1, 3, which corresponds to 1, 2. Each subsequence will be processed separately to determine the minimum operations required. For the first subsequence, 4, 5, 6, we apply the LNDS algorithm. Starting with an empty list, we add 4, then 5, and finally 6. The LNDS in this case is 4, 5, 6, which has a length of 3. Since the subsequence length and the LNDS length are the same, no operations are needed here. Next, for the second subsequence, 1, 2, we follow the same process. We add 1 to the LNDS, then add 2, resulting in 1, 2, as the LNDS. Its length is 2, which matches the subsequence length, so again, no operations are required. Adding the results from both subsequences, the total number of operations for this example is 0. Now, consider the third example where the array is 3, 1, 2, 1, 3, and k is 2. Here, the first subsequence includes indices 0, 2, 4, which gives 3, 2, 3, and the second subsequence includes indices 1, 3, which gives 1, 1. For the first subsequence, 3, 2, 3, we find the LNDS by starting with an empty list. First, we add 3. Then, we replace 3 with 2 because 2 is smaller. Finally, we add 3 back, resulting in an LNDS of 2, 3, with a length of 2. Since the subsequence length is 3, the number of operations required is 3, 2 equals 1. For the second subsequence, 1, 1, we follow the same process.
We add 1 to the LNDS, then add another 1, resulting in 1, 1, as the LNDS, which has a length of 2. Since the subsequence length is also 2, no operations are needed. Adding the results from both subsequences, the total number of operations for this example is 1 plus 0 equals 1. To summarize, the key to solving this problem is reducing it to finding the LNDS for each subsequence and calculating how many elements need to be modified to match its length. Using efficient methods like binary search allows us to solve this problem quickly. The final outputs for the examples are 4 for the first, 0 for the second, and 1 for the third. To analyze the time complexity of our solution, let's start by breaking it into its main components. First, we have the outer loop, which iterates k times. This loop represents the k groups formed by taking every kth element starting from different starting indices. For example, one group might start at index 0, while another starts at index 1, and so on until k1. Next, within each of these groups, we extract a subsequence by iterating through the array at intervals of k. This involves accessing elements at indices like start plus k, start plus 2k, and so on. In the worst case, these subsequences collectively cover all n elements of the array, which means the total cost of subsequence extraction is O, n. So, the first component of the time complexity comes from these two loops, contributing a cost of O, n, for the entire process of grouping and subsequence extraction. Now let's focus on the next major component of the solution, which is computing the length of the longest non-decreasing subsequence, or LNDS, for each subsequence. This is done using the length of LNDS function, which relies on binary search to maintain an LNDS array. Specifically, the bisect_right operation is used to find the appropriate position for each element, and this operation has a complexity of O log m per element, where m is the size of the LNDS array at any point. When processing a subsequence of size m, this results in a complexity of O m asterisk log m for that subsequence. Since the array is divided into k groups, the total cost of LNDS computation depends on the number of elements processed across all groups. Since there are n elements in total, the combined cost of LNDS computation sums to O n log n/k. Adding this to the cost of subsequence extraction, the dominant terms in the time complexity are O n and O n log n/k, leading to an overall time complexity of O n log n/k. Next, let's examine the space complexity of the solution. The space required is primarily determined by two factors. First, for each of the k groups, we temporarily store a subsequence for processing. The size of any single subsequence is at most n/k, and since we process subsequences one at a time, the space required for this storage at any given moment is O n/k. Second, the LNDS array and the length _LNDS function also contributes to the space complexity. This array stores the current longest non-decreasing subsequence for the subsequence being processed, and its size is similarly bounded by O n/k. Beyond these, additional auxiliary space used by variables and function calls is negligible, contributing only O1. Therefore, when we sum these contributions, the overall space complexity of the solution is O n/k. Let's briefly compare this optimized solution to a naive brute force approach to highlight its efficiency. A naive solution might involve generating all possible valid subsequences for each group and checking each one to find the optimal result. Since a subsequence of size n/k has 2 n/k possible combinations, this approach would result in exponential time complexity. Additionally, checking each subsequence for non-decreasing order adds further computational overhead, making it impractical for large inputs. In contrast, the optimized solution avoids this explosion of possibilities by using the properties of the longest non-decreasing subsequence and binary search. This allows it to achieve a much more efficient time complexity of O n log n/k, regardless of the input size. Notably, the algorithm iterates over the same number of elements and performs the same operations in all cases, so its time complexity remains consistent across best, average, and worst cases. Finally, let's summarize the mathematical reasoning behind the time complexity. Subsequence extraction involves iterating through the array n times, distributed across k groups, which contributes a cost of O n. Next, the LNDS computation for a subsequence of size m on average approximately n/k has a cost of O m log m.
When this is summed across all groups, the LNDS computation adds up to O, n log, n/k. Combining these terms gives us the overall time complexity of O, n log, n/k. As for space complexity, the temporary storage of subsequences in the LNDS array both contribute O, n/k, resulting in a total space complexity of O, n/k. In conclusion, this optimized solution is significantly faster and more space efficient than the brute force approach, making it well suited for handling large inputs efficiently. When tackling this problem, there are a few common mistakes you should be aware of. First, misunderstanding the definition of k increasing can lead to confusion. Some assume it means the array must be strictly increasing by exactly k, or that the difference between elements must always equal k. However, the correct interpretation is that for any index I, the element at position I must be less than or equal to the element at position I plus k. It's about maintaining relative order, not exact numerical differences. Another frequent misstep is overusing brute force. Trying to check all possible subsequences or permutations might seem like a valid approach, but it quickly becomes computationally expensive. With constraints where the array length can reach up to 10 to the power of 5, this leads to exponential time complexity, making it completely infeasible. Lastly, errors with binary search are a common pitfall when implementing the longest non-decreasing subsequence within groups. You need to be precise about how you use methods like bisect_left to find insertion points. A small mistake here can compromise the entire algorithm's correctness. Now, let's consider a few more challenges and insights. Ignoring edge cases is another common issue. For example, you might overlook arrays that are already k-increasing or contain repeated elements. Overcomplicating these scenarios can lead to unnecessary operations and inefficiencies. Inefficient grouping is also something to watch out for. If the array isn't divided into k groups correctly, or if you process groups that overlap, you might miss important constraints or perform redundant computations. A key insight for solving this problem efficiently is to reduce it to finding the minimum number of elements to remove such that each of the k subsequences becomes non-decreasing. This boils down to calculating the longest non-decreasing subsequence for each group. The optimal approach here is to divide the array into k groups based on the indices modulo k, and then solve the LNDS for each group using binary search, which gives you an O, n log n solution. Keep in mind, though, that while this is efficient, it requires careful implementation. For example, dynamic programming offers a simpler alternative, but its O, n squared complexity makes it impractical for large arrays. When explaining your approach in an interview, it's also helpful to discuss how you'd optimize your solution for scalability and edge cases, as this highlights your ability to handle real-world constraints. There are several related problems that share similar concepts and can help you deepen your understanding of this problem. For instance, LeetCode 300, which focuses on finding the longest increasing subsequence, directly ties into the LNDS concept used here. It can be solved with either binary search or dynamic programming. Another related problem is LeetCode 1713, which involves transforming one sequence into another with the minimum number of edits. This problem also emphasizes minimizing changes to achieve a desired order. LeetCode 354, the Russian doll envelopes problem, combines sorting with LNDS to solve a nested subsequence challenge, making it another great example of how these techniques can be applied. Finally, LeetCode 673, which asks for the number of longest increasing subsequences, builds on the LNDS idea but adds the additional complexity of counting. Exploring these problems will give you a broader perspective on the techniques and variations associated with subsequence-related challenges. Finally, let's discuss some alternative approaches to solving this problem and their trade-offs. The first is dynamic programming, which has a time complexity of O, n squared. This method is simpler to understand and implement, making it a great choice for smaller arrays or as a preliminary solution during an interview. However, it becomes inefficient for large arrays, especially when n approaches 10 to the power of 5, as it will exceed time limits. A more efficient alternative is the greedy approach combined with binary search. This method operates in O, n log n, and leverages bisect_left to maintain the longest non-decreasing subsequence within each group. While this approach is highly scalable, it requires a solid grasp of binary search mechanics, and debugging edge cases can be challenging. For those looking to explore advanced techniques, segment trees or Fenwick trees offer a way to perform efficient range queries and updates for LNDS. However, these structures are more complex to implement and might be overkill for this specific problem. Each approach has its advantages and trade-offs, so understanding the constraints and choosing the right method is key to solving the problem effectively. Thank you for watching this walkthrough of LeetCode problem number 2111, minimum operations to make the array k increasing. We explored the problem, broke it down into manageable steps, and implemented an efficient solution. Remember to practice similar problems to strengthen your skills. If you enjoyed this video, please like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!